Okay. Hello everybody, my name is Adhisakti Sahasrara Nugroho, and today I will be showing you my Maths for Economics 2 final exam. Okay, so question 1. We want to investigate the behavior price in the market with the demand and supply functions of dt, this one, and st, this one, where dt, st, and pt are demand, supply, and price at time t, respectively. By assuming market clearing in each period dt equals xt and the starting price of at, we have to determine the difference equation that represents the relationship between pt and pt minus 1 and interpret your equation. Then solve the equation obtained in A and then investigate the stability of the equilibrium from the difference equation here. So first, we must lay out what's given to us. So we know that the demand at time t is 90 minus 0.8 pt, and supply at time t is -6 plus 0.2 price at the period before. The t minus 1 annotates the period before. So at the price at time 0, or the starting price, is 80, and we also know that dt is equals to st, which is the clearing solution. Okay, now that we know all that, we can try and do part A, which is determine the difference equation that represents the relationship between pt and pt minus 1. And now we have to interpret the equation. So first we must set dt equals to st, which will give us this long equation here, 90 minus 0.8 pt equals to -6 plus 0.2 pt minus 1. So from here, we can just solve. This is just solving. This is just solving and simplifying to create this difference equation of pt equals to 120 minus 0.25 pt minus 1. So this right here is our difference equation. So now we can take this difference equation and then we can interpret it. And what can we actually interpret from this difference equation is that the market price for an unspecified good, pt, in the current period would always be 120 minus a quarter of the price in the last period. A quarter being 1/4 or 0.25, of course, in the last period. So, for example, if a fish, let's say pt is the cost of a fish, if a fish costs 100 in the last period, the price of the fish in the current period would be right here. So let's pretend that 100 is P1. So right here, the price of fish now, which is P2, is going to be 120 minus 0.25 times 100, and we can solve that and we can get 95. So this, therefore, we can use this difference equation to predict the supply and demand of the good year by year, as well as, of course, the price. Now that we know our difference equation and we already know the function of our difference equation, we can now find a general solution for it. So for this, we can find a solution for it. So for this, we can use the iterative method or the general solution method. I will use the general solution method because it is a more simple method compared to the iterative method, which is more long. But anyway, first we must set the difference equation into this format, which is this format right here, yt plus 1 equals to ayt plus c, under the condition that y0 is equal to b. And after we already set our difference equation into this format right here, and we know that the y0 or starting y over here should be actually starting p, so p0 equals to 80. We can then input this into our general solution, which is generally this right here, yt equals to yh plus ye, but in our case, we use this one right here, pt equals to ph plus pe, where pH, this one, is the homogeneous solution, and pe here is the equilibrium solution. So we can combine these together to get this general solution formula right here. And when we input all of our information in, it will become pt equals to b times -0.25 to the power of t plus 120 over 1 minus -0.25. Sorry, there's a missing bracket there. So in the end, we can find that we have a general solution of pt equals to b times -0.25 to the power of t plus 96, where 96 here is our 96 here is equal to our equilibrium solution, so PE. Right here, this 96 equals to PE. Anyway, so we can still see that here we still have a B. So we need to, of course, solve that. So AT, which is our starting P, P0, is equal to this formula right here when it is equal to, when time T equals to 0, of course. So AT equals to B times negative 0.25 to the power of 0 plus 96, which is AT equals to AT equals to B plus 96, which in turn gives us B equals to negative 16, which gives us our completed solution of PT equals to negative 16 times negative 0.25 to the power of T plus 96. So we actually need to prove the solution quickly, so we know that it's correct. So we can do this by comparing with the iterative method. So right here, iterative method on the left, general solution on the right. We know that P0 is 80, and then P1, using the iterative method, is 100. Using the general solution, is also 100. Same thing for P2, same thing for P3, and therefore onwards would be the same. So we know that our general solution is correct. Now, we can investigate the stability of the equilibrium price in the market and interpret your results. So since we know PE is equal to 96, right here, PE is equal to 96, and also alpha is equal to negative 0.25. Alpha is actually determined by, if I was not mistaken, it's 0.2 divided by negative 0.8. We get this from the beginning, actually, from our dt and ds right here. So these two, we divide them with each other, and then we get our alpha. So from our alpha, we can interpret, the first thing we can interpret is that the alpha is smaller than 0, which means the time path is oscillatory. I'll show you later what that means. And then 2, the absolute value of alpha is smaller than 1, which means the equilibrium state is stable. So we know that the time path is oscillatory and the equilibrium is stable. So this means, so finally we can the final interpretation is this means that the price of the good in the difference equation will continue to converge, which means it's stable, while oscillating towards the long-term equilibrium price of PE equals to 96. To better illustrate that, we can assume that this is, illustrate this is our price right here, and this is our time. And for whatever good this is, for let's say fish, again, let's say fish, the price of fish will continue to oscillate every single period. However, it will slowly trend towards the long-term equilibrium solution of PE equals to 96. We can assume 96, maybe dollars, whatever. So over time, it will keep oscillating, so up and down. It'll go up and down, up and down, up and down, until eventually it will meet at this line, PE equals to 96. Now, for question 2. Suppose that the aggregate output, YT, is given by YT equals to the square root of KT, where KT is capital stock at time T, and capital stock evolves over time with this equation right here, this difference equation right here, where delta is the capital depreciation and IT is the investment at time T. The economy saves a constant proportion S every output period, thus ST is SYT, and ST is equals to IT, and we also know that delta is 0.1 and S equals to 0.3. So from here, we must derive a nonlinear difference equation in capital stock, find all the equilibrium solutions, investigate the stability and equilibrium solutions, and then interpret our results. So first, let's lay out what's given to us. So we know that the YT, which is aggregate output, is square root of KT, which we can write in the form of KT to the power of 1 over 2. And we also know this equation, which is KT plus 1 equals to 1 minus delta KT plus IT. And IT right here can actually be substituted out for ST, which can be substituted out for SYT, which in turn give us 0.3 kt 1 over 2, because we know that s is 0.3, and we know yt here is kt 1 over 2. So to derive a nonlinear difference equation in capital stock, using the info from last slide right here, we can create a nonlinear difference equation of this right here, fk, oops, sorry. So, okay, that line is there, so sorry. So fk equals to 0.9k plus 0.3k 1 over 2. This again, this is from this right here, 0.3 kt 1 over 2, and 0.9k is obviously 1 minus delta, and we know that delta is 0.1, so 0.9k. So now B, find all the equilibrium solutions of the equation obtained in A. To find all the equilibrium solutions, we must sub Fk with Ke. So Fk equals to 0.9k plus 0.3k 1 over 2. We can sub Ke in for k, and this will give us this will give us Ke equals to 0.9 Ke plus 0.3 Ke 1 over 2. We do some solving, so we shift this on this side, and then simplify until we get this equation right here, Ke in brackets 0.1 minus 0.3 Ke negative 1 over 2. From here we can solve Ke. The first solution for Ke is 0, and then the second solution for Ke is 0.3 Ke negative 1 over 2 equals to 0.1, which will in turn in the end give us Ke equals to 9. So this is just the solving right here. We get Ke equals to 0 and Ke equals to 9. So now to investigate the stabilities that we found in B, so these two stabilities right here. In order to investigate the stabilities, we must remember the rule y dot equals to ye equals to a. So basically the first derivative, or we can also write that as the first derivative of ye equals to a. And from a, alpha, we can determine if it's bigger, smaller, to 0, which will give us the stability, yeah. So to get the value of a to investigate stability, we must first, So fk, so first we derive our fk into the first derivative right here. So this is what we're going to use for testing, which is 0.9 plus 0.15 k negative 1 over 2. So for the first equilibrium solution for k, which is 0, we can input that into our first derivative, and it will give us actually a non-applicable, unfound, non-applicable solution. So this equilibrium solution we just ignore. But for the equilibrium solution of 9, when we input that into our first derivative, we actually get a stability, an A value of 0.95. So what can we interpret from these two results? So the first thing we're going to interpret is for the solution, for the equilibrium solution of Ke equals to 0, A equals to 0. Which is A equals to 0.9, blah, 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 we cannot define it. So therefore, we can interpret that capital stock in the economy will never be Ke equals to 0. This will never happen. It's impossible. So no matter the YT aggregate output, it will never happen. However, for the solution Ke equals to 9, we are able to reach an A of 0.95. An A of 0.95 is smaller than 0, which means it is non-oscillatory, and 0.95 is bigger than 0, which means it is non-oscillatory, and then the absolute value of 0.95 is smaller than 1, meaning stable. So this means we can conclude that capital stock K, based on the aggregate output YT, will eventually reach a long-term equilibrium of Ke equals to 9 without an oscillating time pattern. This can be illustrated right here. For equilibrium solution Ke equals to 9, every single time K1, K2, let's just say K1, K2, K3, and onwards will keep on trending towards the long-term equilibrium of 9 right here without oscillating. Okay. Yeah. Okay. So now on to question 3. This is a government question. So can the government run on a persistent budget deficit? and can can debt grow forever without bankrupting the nation? So to find out this, let DT, YT, and R be the amount of debt at year T, national income in year T, and interest rate year by year respectively, with D0 equals to 0 and Y0 equals to 1. Here, bankruptcy means that whether the ratio of interest payment to the national income will exceed 1, for example, which means RDT over YT is bigger or equal to 1 at some year. Suppose that the time path of income is given by Y dot equals to GYT, and the time path of the debt is D dot equals to BYT. Let's pretend you're the government, and we are informed that R equals to this, D equals to this, and we need to find, this is the important part, we need to find a target income growth G to avoid the country from bankruptcy. Okay, so first let's lay out what's given to us. We know that, we know that the Y dot value is GYT, and the D dot value is BYT. So from here, we also know that we need to figure out the value of G in this this little ratio, or this let's say solving solution. The solving solution, we need to find the value of G in this solving solution to make it not larger or equal to 1. So first, we need to find the values of dt and yt, and in order to do that, we need to solve d dot and y dot. So first, we can solve y dot, since y dot has y in the equation itself. We can straight away use the E rule in order to integrate it one time. So we can instantly get from y dot to yt equals to a e gt. Right here. So basically, we move the G up, E, and then put the A in front. And also, since we know that Y0 right here, sorry, Y0 is equal to 1. So when Y0 equal to 1, AE0 equal to 1. So we know that A is equal to 1. Therefore, we can conclude that YT is just EGT. Okay, so now that we know that YT is equal to EGT, we can I erase this now? Sorry. So okay, yeah. So now that we know that YT is equal to EGT, we can solve our D dot solution. But since we do not have, by subbing in EGT into the D dot formula right here, and since this this equation does not have a D, like a D value in it, we will have to manually integrate it using the dd over dt equals to be gt, move over the dt, and then from here, once we have it in this form, we can straight away integrate it. We use s as like just a placeholder value, and 0. So ddd integrate the power of s and 0, and then degt integrate s and 0. We will get this, and let's just speed through this. So we will get this simplified. We will get ds equals to b over g, egs minus b over g. We can take out the b over g here and get, in the end, we will get the solution. We will get not the solution, but we can get the the equation dt equals to b over g times e gt minus 1. So now we have our dt value, and we also have our yt value. So now that we know our dt and yt values, we can input this into our dt over yt equation. So our dt over yt equals to r b over g e gt minus 1 over e gt. We can simplify this here and here in order to get this equation right here, which we will use to find our g value right here. So what does this equation tell us? So this equation tells us that the steady state value, or the determining value of r dt yt is actually rbg right here, because this is the variable part of the equation. This right here is relatively stable, while this right here is the variable part. So as long as rb right here is larger than g, because rb over g, the value of RDT over YT will be smaller than 1. So we can conclude that if RB is smaller than G, the country won't go bankrupt, and otherwise it does. So therefore, we can use this rule that we have obtained to find a suitable value of G. So when R equals to 5% and B equals to 0.1, RBG is equal to 0.05 times 0.1, and it will become 0.05 over G. So this means in order for our country to not go in bankruptcy, we must sustain an income growth rate of G larger than 0.5% or G larger than 0.005 every period to avoid bankruptcy. So G as in growth rate has to be, we can go for 1%, 2%, anything as long as it is over 0.05 right here. Now, question 4. Explain the concept of stability of equilibrium point in a nonlinear first-order differential equation. Briefly provide an example in economics, business, or finance. So first, to explain the concept of stability and equilibrium in nonlinear differential equations. First, let's take a look at the linear differential equations first. So a linear differential equation, we have this as our sort of placeholder equation. So y dot equals to ay plus b. From here, we can obtain general solution, of course. General solution is actually not that important. For explaining, we just need to understand that ye will always be equal to ye is equal to big A, and ye will always be 0 as well in a differential equation. This does not change. So now we can compare linear versus nonlinear. So linear, y dot equals to ay plus b. We can write this as well as y dot equals to f, f as any function, f as a function of ay plus b. Sorry, not any function, f as a function of ay plus b with the y in the brackets. Meanwhile, a nonlinear differential equation will be the same as this. However, f can be any function, So it does not have to follow the rule of ay plus b. So it can be, y3 plus y4, whatever. It can follow anything. It doesn't have to be ay plus b. And also, general solution is very hard to find / impossible to find for a nonlinear differential equation. So we do not bother with finding general solution. So now we know for a nonlinear differential equation, y dot equals to fy in brackets. And also we have the condition y0 is equal to k. K is our starting value of y. And we also know the equilibrium solution ye is equal to 0. This means ye equal to 0, and this also means f equal to ye, which also means f equals to ye equals to 0. Now that we know all of this, since we can't find an alpha solution from the general solution in a nonlinear case, we have to investigate the stability using the first derivative of ye. So first derivative of the function f with ye inputted into it. So when the first derivative of f with ye inputted into it is smaller than 0, ye will be stable right here. And if the first derivative is bigger than 0, ye will be unstable. And we must keep in mind that there can be multiple ye's for nonlinear differential equations, or maybe there are none, or maybe it can be like anything. It can be 1 ye, 2 ye, anything. Of course, the stability and the instability will mean, as we know, stable is trending towards ye, unstable trending away from ye. However, since we cannot find the a, we do not know a of these time paths, we cannot conclude if the values every single period is oscillating or non-oscillating. So we don't know if it's going to go up, down, or if it's going to keep going down, up, whatever, we don't know. Now that I explained briefly about the theory of nonlinear differential equations, now I can give a brief example. In the market for fish, again, we use the fish example, the total market output, F, for fish is decided by F equals to S plus T, where S is salmon and T is tuna. And S and T are decided by these equations right here. So salmon is this one, tuna is this one. So to find the equilibrium solutions, first we must derive, of course, a differential equation, F equals to 400 pt square plus 300 pt. And we can change this into the form y dot equals to 400 y squared plus 300 y. Same thing. From here, we can find our ye. Let ye be the equilibrium solution. So 400 ye squared plus 300 ye equals to 0, as we know from before. Ye is always equal to 0, same thing as the differential equation, the regular linear differential equation. So, okay, right here, ye equals to 0. So we can, from here we can derive the ye solutions of 0 and ye solution of negative 0.75. To investigate stability, we must simply find the first derivative of the function in y. So first derivative of function in y we can obtain is 800y plus 300 from our first solution here. And now from here we can test our ye values. So for the ye value of 0, we input it in. We actually get a ye right here of 300. We can get a stability of 300, which is larger than 0. This means ye equals to 0 is unstable solution. It's an unstable solution, therefore, in the long run, it will go away from 300 right here. It'll go away from 300. Meanwhile, for ye equals negative 0.75, when we input it into our first order derivative of f, we will get negative 300. This means ye negative 0.75 is stable, since it is here, this value here is smaller than 0. So for ye equals to negative 300, it will instead go closer towards it. And that's all for my presentation. I hope it's clear, it's good, and thank you.